Hello, everyone, and welcome to the class notes for AP Statistics covering the central limit theorem of statistics. You can see this opening sentence here, the mean of the sampling distribution of sample means. If you understand that, then you've read the textbook like you were supposed to before you watch this video, and you have a good idea what's going on. If this is totally foreign to you, go read the textbook first, come back, and then take a look at this. But I'll try to explain a little bit and try to look at the highlights. Make sure, you are studying this before the video. This video is only to make sure that I hit kind of the highlights of the unit or the chapter. Okay, so the mean of the sampling distribution of sample means. Well, this lesson is actually the opener to the whole second semester of statistics. It's where we start doing inference. And the whole idea in inference is when, in the real world, you're going to go take a sample and you're trying to find out what the truth is from the population. The trouble is you can never, like most of the time, you can never really do a census and you're never going to know what the real truth is. You can only do a sample from the population. And then we use our statistics to try to estimate or model what the truth might be, even though we'll never know for sure what it is. We can use our probability and what we know to be true to come up with some kind of good estimates. Like, I'm pretty sure the mean of the population is in between here somewhere, right? Or the proportion of the population is in this range somewhere. So we're going to be doing things like confidence intervals. It has the word confidence and interval. The confidence is the probability, and then the interval is going to tell you where we think the truth is. So you're going to hear things like, I'm 90% confident that the true mean length of the certain type of fish is between 26 and 32 centimeters, right? And that's the best we're going to be able to do in statistics. What this lesson is kind of introducing the tools you're going to need to do all this inference throughout the rest of the semester. So it really is a big unit, and it's worth listening to all this in the video. Sorry if it goes long, but it's useful stuff. So what this the mean of the sampling distribution of means. So how the whole tools of statistics works is that normally we just take one sample, and then from that sample, we're trying to figure out what the truth is. But in order to understand that, we pretend like that we're going to take many, many samples. And then we say, how does the mean behave? Because usually we're looking for the center of our data. So how does that center behave? Does it have a wide, a lot of variation to it? Does it have a wide range of variation? Or is it, does it really, like, does the mean of a sample, is it always really, really close to the mean of the population? Like, how accurate do we need to be, right? So I think I'm going to go right into the applet here that I have. This is a cool little applet. So here, imagine this normal curve you see here is the whole true population. And this is the truth. Like maybe it's I don't know. Let's just make up the weight of a dog. Okay, a certain type of dog. All right. So you have these dogs, and they weigh different amounts. You have some that weigh more, some that weigh less. But there is a truth. You see this little red thing here, right in there. There is a truth for the actual mean of all dogs in the whole population, right? There is that truth. So we're looking for that, but we're never going to do a census, and we're never going to know what this really is. So we're looking at when we take our sample. Here, I'm going to take a sample. So let's say I sample 5 dogs. Boom. 1, 2, 3, 4, 5. I get my 5 dogs. I take the mean of my sample, and I get this little blue dot. This blue dot is the mean of my sample. And this is where I think the true population is. But you can see that the true population is just a little bit less than what I got in my sample. And the other thing to notice is that the individual dogs in my sample that has a lot of variation, right? But the mean of those dogs is pretty close to the mean of the population. So this is what we're looking at. So this is just a distribution of my sample. The sampling, this is the sampling distribution, the distribution of my one sample. I'm going to do a distribution of a bunch of means. So a bunch of samples. So I'm going to do the sampling distribution. So let me do it again. What if I took a different sample? Okay, because remember, you're only going to do one sample in the real world. You're not going to do many, many samples. You're just going to do the one sample, and you're going to get that one mean. So we're just trying to see how this mean behaves. If I were to do many samples, which you're not going to, but we want to, it's just for practice, or to see how the formulas work and how what we can do to have confidence about our mean. Okay, so this sample had a lot of variety again in the individual dogs, but the mean of that sample was really like spot on to the truth. Let's do another sample. Right? Now that one was a little off, that mean was a little off. So when you do your sample in the real world, you only get one shot. This possibly, you could end up with something that's off from the truth, right? And we're not going to know if we're right on the truth, if we're higher than the truth, or if our mean from our sample is lower than the truth. We're not going to know. Let me do another one, and another one, and five more, and five more, and five more, and five more, and five more. Boom, boom, boom. And I'm going to do more, and keep going. You can see that you get a variety, right? Sometimes the mean you got in your sample is just way too big. Sometimes it's way too small. Most of them are going to be pretty close. But what we're going to do is say, well, let's say I got one of these means, right, from in my sample. So instead of saying this is the truth, I'm not going to be that naive and think that whatever I got in my sample is the truth. We're not going to do that. What we're going to do instead is we're going to say, we're going to make this thing called an interval. And we're going to say, I don't know for sure where the mean is, but I'm pretty sure the true mean is in this interval somewhere. The question is, how big of an interval do I need to have? Well, it goes with your confidence. And we'll talk about intervals more later. I don't want to get into that too much. But it goes with the confidence. The smaller the interval, the less confident you are it's going to be in there. If I make this little teeny interval, I'm not going to be very confident that the true mean is in that interval. If I make a really big interval, I'm going to be pretty confident that the true mean falls in that interval, right? So by doing this little simulation here, we're just getting an idea of how the means get distributed, right? When I did one sample, ooh, that's a good example right there. See how the spread is really big spread, right? Just from one sample. But the means themselves don't have a lot of spread. Like this standard deviation, the standard deviation of this is probably only about that big. So, that's only half of that is the standard deviation. So this has a pretty small standard deviation compared to this sample has probably a pretty big standard deviation, right? For the individual pieces. But the mean itself has a smaller standard deviation. Most means from your samples will be pretty close to the mean of your of the truth, right? Of the population. Now, the other thing I want you to notice, so let me do 10,000, bang, is if you do a bunch of these, this will always turn out to be a normal curve in shape, normal in shape. So we know that when I take a mean from a sample, right, sample, and I take a mean from that, I know that the mean itself, the means themselves, have a normal shape. And I can use a normal model to represent the means. Just like maybe if I did a sample that was bigger up here, instead of just a sample of 5, right? 1, 2, 3, 4, 5, I could, normally this is going to have its own normal curve, but we're going to have a normal curve for the means as well. And this is what we're working with. We're using a normal curve on the means in this unit. All right. So let's go back to the notes and look for a few highlights. Whoops, back here. Okay, so the mean of the sampling distribution of the means. So we took the means from a whole bunch of samples, and then we were looking at the mean of those, right? The mean of those, this will equal the truth, the true mean of the whole population. If I took the mean of a whole bunch of means, if that makes sense, right? If I took, sorry, I'll go back to this just to, right? If I took the mean of this distribution, it's going to be pretty much spot on the truth. And that's what this is saying. Okay, that's what this is saying. All right, moving on. Main points. It works for proportions as well as means, right? So this is the fundamental theorem of statistics. That's what you just got done looking at. The sampling distribution is normal in shape. It works for proportions. It works for means as well. So discrete and continuous data. For the proportion set of it, you're going to need a couple things. These are your two tools, right? The whatever our center of our, you see the little hat here on this? The little hat there tells you it's the sample, and then without the hat is the truth. So the mean of all my samples is the true mean, right? That's what this is saying. And the standard deviation of my samples is my proportion times the 1 minus the proportion, so like 0.2 times 0.8 or something, divided by my sample size. Now this is what is new to us, dividing by n. Why are we dividing by n? Because we're looking for an average of a bunch of samples. That's what you're imagining, of a sample size, right? The bigger your sample size, the closer your center will be to the truth. So this is like an average. So you're dividing by n to get an average of that. But you're going to need kind of these two formulas, right? This PQ over n, the square root of that. We're going to use that a lot this semester, right? It follows a distribution, a normal distribution, as we've said already. And then the new thing that we got to really start thinking about, we've talked about conditions in different sections a little bit, but this is where we really start saying you have to check your conditions before you can use those formulas and do your intervals and look for the truth. Okay, so let's talk about conditions real quick. The whole idea is you want to make sure that there's nothing affecting your results, right? When you take your sample from the population, you just want to make sure that's a good sample. It needs to represent the whole population, right? You don't want a sample that underrepresents your population, then your results are just going to be off, right? So these first two, the independence and the randomization conditions, just kind of assume like, if I measure one thing and maybe I remove it from the population because I measured it, it's not changing the overall probabilities in the whole population. So we got to make sure that each of our subjects or things that we draw from the population are independent of each other. Those probabilities don't affect each other, and my probabilities stay consistent as I'm doing my sampling. We want to make sure it's random, of course. You want to make sure all groups in that whole population are accounted for. So these kind of go together just to make sure you have a good sample. And then the next piece is the sample size. For proportions, we want the number of successes, so the n times p. We want that, and we also want the n times q to be bigger than 10. The idea is that if you don't, like, let's say I did a proportion thing, and I'm checking to see, how many people are Democrats and Republicans or whatever, and I start sampling people, and I just get Democrat, 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 and I haven't got any Republicans yet. I might think in my population there's no Republicans, but I'm like, well, I know there's some Republicans out there, right? I just need to know what percentage that is. So you have to keep going, and you got to get just a big enough sample size so that not only the Democrats and the Republicans are represented in your sample, right? You don't want to leave a group out. So you want the failures and the successes to be bigger than 10, right? The expected number, right? Okay, so n times p is bigger than 10, n times q is bigger than 10. So if I expect there to be 70% Democrats at ASIJ and 30% Republican, and I'm going to sample 100 people, then 70% times 100 would be 70 people. That's going to work. And then I would do 30% times 100, which is going to be 30 people, which would be bigger than 10 as well. That would work, right? So that's kind of what you're doing. And we'll go through problems in class, so I'm not going to get into the nitty-gritty of it too much. I'm just trying to point out the big picture. Okay, 10% condition. This is a little bit weird. You got to check it, though. You actually don't want your sample size to be too big, and that's what this is about. If let's say you have a population I don't know, like ASIJ has 1,600 students, right? So if I sample more than 160 of the students, I'm actually getting so close to a census. I know it doesn't feel like it, but you don't want to go more than 10%. The statistics that we're using for this rely on that you're just doing a sample from a population and you're not taking out a big chunk of your population. If you get a really big sample size, like so big that it's bigger than 10% of your population, the probabilities in your population and what you're choosing from are likely to change. Like you're not ensuring those probabilities stay the same throughout your sample, because your samples are just so big that you're getting closer and closer to a census than you are a real sample. Okay, so we got to check these conditions. A lot of times we'll do the IR together, and then we have to check the sample size and we have to check the 10% condition. I always remember the acronym IRS 10, like IRS from the Internal Revenue Service, and then like a 10% tax or something. So IRS 10, remember this, put it in your brain for the rest of the semester and then for your life. IRS 10. We're going to have this in different variations, but it's going to be pretty much IRS 10 for a long time. All right, so that's for proportions. It's very similar. You can see in the notes here that, they go through all that, what we already did. I'm going to go all the way down. Here's for means. Same thing, independence, randomization, and your sample size. Now for the means, they don't really have a formula you have to check. You just have to say you have a big sample size. Well, how big is it big enough? Well, it depends on what you expect to kind of see and what to measure. Usually 30, 50 is big enough. 50 is a good way to go. If you go more than 50, that's fine. But again, you have to make sure you're less than 10% of the population. Otherwise, what you're looking at changes, right? The randomness changes. Okay, so still independent samples, random samples. Sample size just needs to be big. 50 is good. Below 30, it's getting too small. Up to 100 is great. But you don't want to go too big. Okay, so very similar to the means and the proportions, what you're checking for your conditions. Now, once you have your conditions, you can use your formulas. Now, we looked at the formula for the proportion already. This is the formula for the means, right? Look how the standard deviation is the standard deviation you get divided by the square root of n now. This is taking an average. And the reason we're doing that, let me show you one more time. The reason we're taking our standard deviation and dividing by something is we don't want the standard deviation from the sample, which was really big, right? We want the standard deviation for the means, which is really small. So we have to take our standard deviation we had and make it smaller by dividing by the square root of n. Why we do it exactly this way is another question. That's the mathematics you have to get into. Don't worry about it. You just need to know how to use the formula. Okay, the mean stays the same. It's just the standard deviation gets adjusted because now you're looking for the means. You're not looking for an individual dog. You're looking for the average weight or height or of whatever of a dog, okay? Of all dogs, right? Okay, so that formula you need, the proportion formulas up above, right there. You need those. And then the conditions as well. Everything else works like a normal model. So once you get your mean and your standard deviation, everything else, z-scores and probabilities, norm CDF, all those things work just the same as what we had in the past. So look for videos that have to do with problems so you can see how these work in action. But that's the big picture. Thank you and see you next time.